It is January 2026, and what we knew as the cloud is dead. Or rather, it has evolved into something entirely different, something much more physical, dense, and voracious. What we are witnessing in the United States is no longer the construction of simple data centers where we store our photos or host web pages. We are facing the birth of AI factories. I'm passionate about how engineering shapes our reality, and welcome to the next engineering framework. Today, we're going to break down a fascinating technical report on critical infrastructure in the United States between 2025 and 2026. We're going to talk about thermodynamics, photonics, gigawatts, and how the geography of technology is radically changing. Let's start with the fundamental problem: density. Until just a few years ago, let's say 2022, if you walk down the aisle of a standard data center, each rack, those black cabinets full of servers, consumed between 10 and 15 kilowatts. It was manageable. You could cool it with powerful air conditioning. But then came the large language models, the trillion-parameter class LLMs, and with them, the need for brutal hardware like NVIDIA H100 and H200 accelerators and the Blackwell architecture. Today, in 2026, that same rack no longer consumes 15 kilowatts. We are talking about densities of 100 to 120 kilowatts per rack. And if we look at the most aggressive integrations, like the NVL72 clusters, we are projecting towards a megawatt per rack. This is thermodynamic madness. We have hit the power density wall head-on. Air no longer works. Air is a terrible conductor of heat when you have that much energy concentrated in 5 or 3 nanometer silicon. This brings us to the first major paradigm shift. The CPU is no longer king. In these new AI factories, the CPU is just a manager, a head node that organizes the work. The real workers, the worker nodes, are the GPUs, TPUs, or LPUs. And here, efficiency isn't measured in raw operations per second, but in a metric called MFU, or model flops utilization. What does this depend on? On the chips not burning out and being able to talk to each other instantly. Let's analyze how the tech giants have solved, or are trying to solve, this engineering puzzle, because each has taken a different and fascinating path. First, let's travel to Mount Pleasant, Wisconsin. There, on land that formerly belonged to Foxconn, Microsoft and OpenAI are building Project Fairwater. This campus is the perfect example of the distributed supercomputer. What Microsoft is doing here is a masterpiece of integration. They are massively deploying NVIDIA silicon, yes, but also their own chip, the Maya 100, designed specifically so that when you talk to ChatGPT, the inference is fast and cheap. But the critical factor here is cooling. Microsoft has said goodbye to traditional air systems, the cracks, and implemented what they call liquid cooling sidekicks. Imagine this. Instead of cooling the room, they bring the liquid directly to the rear door of the rack, or, via cold plates, directly to the chip. We are talking about capturing heat at the source. This is vital because these chips have a TDP, a thermal design power, exceeding 700 watts. If you don't extract that heat immediately, the silicon degrades or shuts down. Furthermore, they have woven a neural network of cables using InfiniBand topology that is already jumping from 400 gigabits per second to 800 gigabits per second. It is a data highway with no traffic lights. In second place, we have to talk about brute force and execution speed. We have to talk about XAI and its Colossus cluster in Memphis, Tennessee. Elon Musk and his team took an old appliance factory and turned it into the most powerful training cluster of 2025 in record time. They started with 100,000 H100 GPUs and are now integrating another 100,000 units, mixing H100s and H200s. Their goal is to reach 1 million GPUs. But here lies a very interesting engineering decision regarding the network. Unlike Microsoft, which uses InfiniBand, XAI opted for Ethernet, specifically NVIDIA's Spectrum-X architecture. Why? To reduce dependence on proprietary switches and lower costs while maintaining low latency through a protocol called RDMA over Converged Ethernet. It is a risky bet for massive training, but it allows them to scale quickly. However, XAI's challenge was power. They needed 150 megawatts right then and there. The local electrical grid couldn't provide it that fast. The engineering solution? They deployed a farm of mobile gas turbine generators and Tesla Megapack battery banks to smooth out the peaks. It is an industrial brute force solution. And it is not without technical controversy. Their evaporation towers to cool all this consume up to 1 million gallons of water a day. This has forced the design of on-site gray water recycling plants, because engineering is not just electronics, it is water resource management. In third place, let's look at a totally different approach. Google in Iowa. Google has always played in a league of its own. While everyone fights over NVIDIA GPUs, Google has spent years perfecting its TPUs, tensor processing units, now in their Trillium version. But the true jewel of Google's engineering, the thing that really excites me as a photonics enthusiast, is their OCS, optical circuit switching. Let me use an analogy here so you can understand the magnitude of this. In a traditional switch, the light signal coming through the optical fiber has to be converted into electricity, processed by the switch chip, and converted back into light to continue its path. It's as if on a highway, every car had to stop, the driver had to get out, register at a checkpoint, and get back in to continue. That adds latency and consumes energy. Google has eliminated that. Their Apollo project uses microscopic mirrors, MEMS, that physically move to redirect beams of pure light from one TPU to another. There is no conversion to electricity in between. It is light bouncing off mirrors. This allows the network topology to be reconfigured in real time. If an AI job needs a different network structure, the mirrors move, and the light changes paths. It is elegant, it is efficient, and it drastically reduces energy consumption. Furthermore, Google has standardized liquid cooling with its Project Deschutes, releasing the designs so the industry can move forward. Fourth, we cannot ignore Meta in Louisiana. Mark Zuckerberg canceled entire projects to redesign their centers under an AI-first philosophy. Meta is doing something very brave, direct-to-chip, DTC, liquid cooling, eliminating the raised access floor. And note this detail. They use water at 30 degrees Celsius, 86 degrees Fahrenheit. Traditionally, very cold water was used at 7 or 10 degrees. But by using water at 30 degrees, which is still much cooler than a chip at 80 degrees, they spend much less energy cooling that water. Their power usage effectiveness, PUE, is close to 1.05, which is almost perfect. But the most impressive thing about Meta is their long-term energy vision. They know the electrical grid is not reliable enough to train Llama 4 or Llama 5 without interruptions. That is why they have signed deals to explore small modular reactors, SMRs. They are seeking nuclear energy independence for their $10 billion campuses. Nuclear engineering is merging with software engineering. And finally, in fifth place, a special mention to Tesla and their Dojo project in Texas and New York. Tesla does not use conventional chips. Their D1 architecture is based on system-on-wafer. Imagine that instead of cutting the silicon wafer into individual chips and then trying to connect them, they leave 25 chips connected on the same silicon wafer and package the whole thing. They call it a training tile. The density of this is absurd. A single tile consumes 15 kilowatts in a volume smaller than a cubic foot, a large shoebox. There is no slow external RAM. Everything is integrated. This requires extremely complex phase change thermal engineering. And by 2026, they are already transitioning toward the AI6 chip, likely on 3 nanometers, seeking to unify the brain inside the car with the brain training in the data center. Now, let's analyze what all these stories have in common. There is a clear pattern: regionalization. If you look closely, we are no longer talking about Silicon Valley or Northern Virginia, which was the internet capital of the world. Virginia is saturated. There is no more electrical power available. Investment exceeding $100 billion annually is moving to the Rust Belt, Wisconsin, Ohio, and the Deep South, Mississippi. Why? Because there is old industrial infrastructure there, access to water, and robust electrical grids inherited from the manufacturing era. The Rust Belt is becoming the AI Belt. But not everything is rosy. We face critical technical challenges that, if you are engineers or aspire to be, are golden opportunities to solve.
The first challenge is interconnection. Copper is dying. At the speeds we need, electrical signals in copper cables degrade over very short distances. We cannot wire a cluster of 100,000 GPUs with copper alone. The industry is moving towards CPO, co-packaged optics. This means putting the optical transceiver, the laser and the detector, literally stuck next to the GPU in the same package. The problem is that optics hate heat, and GPUs are 1,000-watt space heaters. Putting a heat-sensitive laser next to an oven is a massive thermal management challenge that is not yet fully solved.
The second challenge is water. We have improved energy efficiency, PUE, but we have worsened water usage effectiveness, WUE. Evaporating water to cool gigawatts is unsustainable in a world with water stress. We are seeing a forced transition toward dry coolers, or closed loops. This consumes more electricity, for the fans, but zero water. It is an engineering trade-off. Which resource is scarcer in your location, electrons or H2O molecules? And the third challenge, perhaps the most serious, is power grid latency. And I don't mean data latency, but construction times. It takes between 18 and 24 months to build one of these giant data centers. But it takes between 5 and 7 years to build the new high-voltage transmission lines to bring them power. There is a brutal temporal mismatch. This is forcing companies to become power generators. It is no longer enough to plug into the socket. You have to bring your own gas plant or your own nuclear reactor. In conclusion, artificial intelligence infrastructure in the United States has ceased to be a simple extension of computer science to become a heavy industrial engineering discipline. The success of Microsoft, Google, XAI, or Meta no longer depends solely on whether their algorithms are smart. It depends on their capacity to innovate in thermodynamics, in silicon photonics, and in high-voltage grid management. We are witnessing a geoeconomic reordering where access to massive energy is the new gold. Technically, we have learned today that liquid cooling and optical switching are no longer lab experiments. They are mandatory requirements. Without them, artificial general intelligence, AGI, is physically impossible. It is not just code, it is hardware, it is physics, it is real infrastructure. I hope this tour through the belly of the beast has opened your eyes to the immense physical complexity that sustains AI. And now I throw a question out to you. Seeing that energy is the main bottleneck, do you believe the solution inevitably lies in nuclear energy dedicated to data centers? Or will we see an innovation in algorithm efficiency that reduces this voracious demand? Leave me your opinion in the comments. I am very interested in reading your technical perspectives. And if you want to continue understanding the engineering foundations to build this future, subscribe to the Next Engineering Framework. See you in the next analysis.